Okay, well, it's right around 9 o'clock and I'm here to present a Wednesday webinar for GeoGebra. I'm Karen Camp. I am a math teacher, teacher educator, and technology consultant here in Connecticut. I love to use technology to help students visualize and understand math, and I miss being able to go to conferences and workshops and work with teachers, pre-service and in-service teachers right now during our current situation. Tonight, I'm going to talk to you about the Action-Consequence-Reflection Cycle with GeoGebra activities. And as you can see, we're going to use dynamic graphs and mathematical invariance. And those are two different categories that hopefully I will get through all of that I have planned. Okay, so let me share my screen. And I think you'll be able to see. Here we go. Let's just look at a couple of things. First of all, here's my information. Karen Camp is my name, and @Karen Camp is where you can find me on Twitter. And if you want to email me, it's karen.camp@gmail.com. So what is the Action-Consequence-Reflection Cycle? It is where we have students performing a mathematical action, then they observe a mathematical consequence. Asking them questions: what did you observe? What changes? What stays the same? Those questions allow students to reflect on the result and reason about the underlying mathematical concepts. So this Action-Consequence-Reflection Cycle is based on cognitive science, and dynamic technology like GeoGebra allows students to be engaged in this dynamic environment, this action-consequence-reflection environment. In my opinion, reflection is the key piece. Without that reflection piece, students can do our math tasks, they can remember that they did something in GeoGebra, but they may not remember the math concepts and procedures that we wanted them to learn. So getting all the way through the cycle makes their learning stronger, deeper, more durable, and that's what we're aiming for. Okay, so what we're going to do tonight is I'm going to take you through several ready-made GeoGebra activities, and you can follow along, but don't worry if you can't. All of the slides, handouts, and activities are available for you, and we'll give you all the links. Okay, so where we're going to begin, I'm going to put in the chat the link for the GeoGebra book. Okay, it's a bit.ly link, bit.ly/webinar, uppercase M for May, 27 GGB, and that is a GeoGebra book, and that GeoGebra book brings us to here. And what I've got here is I've got 7 GeoGebra activities. We hopefully will get to see them all, but we'll see how the night goes. Let's begin, actually. Let's begin with power functions. And this was one of the very first action-consequence reflection activities I did. So let's take a look. And let me make this a little bit bigger. Okay, so remember what we're asking students to do. We're asking them to perform a mathematical action and observe a mathematical consequence. And with GeoGebra's dynamic capability for dynamic graphs, we can have a slider where students can observe what's happening while the graph is updating in real time. So this graph is simply graphing a power function, a monomial x to a power. And if we have students begin by engaging with this, all they have to do is drag on the slider, and right now it's x cubed. If we go to x to the 4th, here it looks now, then x to the 5th, 6th, 7th, 8th, and we can go back 7th, 6th, 5th, 4th, 3rd, 2nd. And what I want you to do is imagine, put on your student hat right now and ask yourself, what do you notice? What changes? What stays the same as we change our exponent from 2 to 3 to 4? What do you notice? Is there something in common with some of these graphs? And hopefully you're noticing that the even powers both seem to have their, both parts of the graph are pointing upward. They're more U-shaped, if you will. The odd graphs have this other shape where the left side of the graph is down, the right side is up. But this pre-made file allows students not to worry about the different parts of how to graph it, but it's asking them to notice what's different and what stays the same. So like I said, hopefully you notice that we've got two different shapes. And the other thing that's interesting is that if we change our leading coefficient and use a negative leading coefficient, now we have a different pattern that we can observe. And so I had students working with this to identify the patterns in the end behavior of polynomials. And what's also nice about this is that you can still also go down to a power of 1. Okay, that's still a polynomial, if you will, y equals x, the linear function. What happens if the power is 0? Okay, that might be unusual, that might be unexpected for your students, but you can have a discussion of what a zero power actually does. Anyway, students are going to identify this pattern, and you can see down below that there are some questions here. And the questions are going to also ask students to make predictions. What would be the shape of the graph if the exponent was 11? What if the exponent was 12? Those are outside the range of my slider, but I want students to make a prediction. And this is really very basic. It's just the leading coefficient and the degree, whether the degree is odd or even. And there's so much more that you can do with this. If you go to a graph that allows us to look at the power functions at the same time. So what I'm going to do is I'm going to go to the GeoGebra homepage and just get their graphing calculator. Now, what has just recently hit their homepage is now we have the graphing calculator in the center here and the calculator suite. They are almost the same. The difference is that this graphing calculator is test ready. It is not going to allow certain features that might not be allowed on standardized tests. The calculator suite version of the calculator is a little bit more powerful, but either one will work for us. Let's just take a look at the graph. And actually what I really want to show you here, hold on, is the worksheet that I have students working on. Now, why do I have a worksheet if I have a digital environment for them to work on? Remember that I said that the reflection aspect of the cycle is so important. And in order for students to really think about and ponder what they've seen and notice is they have to take down some notes. They have to perhaps make some conjectures and decide what they think about these things. So I try to always give students a paper copy of something. Maybe it's a lab sheet like this. Perhaps it's just take down some notes in their notebook. Perhaps it's a shared observation sheet with a partner or a group. But here was my end behavior investigation. And if you notice, what I did is I had students say, use the slider to graph these functions. So back here, I would graph the 2, and then I would go to the 4, and then I would go to the 6, and then I could go to the 8. And I wanted students also to pay attention to what is same and different between the squared, 4th, and 6th power. It's a little hard to do here. So on the calculator suite, let's do x squared. And then let's do, let's do, x to the 4th power. And then let's do x to the 6th power. And now we can see all three of these functions graphed together. So here you have a really nice look at what the differences and similarities are. They're all still U-shaped, but the green x squared is a little bit rounder here and not as steep on the outside. Whereas the blue x to the 4th and the red x to the 6th get steeper on the inside, but flatter down below. I wonder why that happens. One of the things that also helps make students' learning more durable is to look at it from different representations. So this isn't just a graph, it's obviously numerical values that we are graphing. So what we're gonna do is we're gonna take our functions here, we're going to put them into a table. And all I did is click on the 3 dots here, table of values. And I want to start at, I want to start at 0 and end at 5. And let's take a look at the table. And I really want all of these in the table, so I'm going to add them to the table. And so let's take a look at what's really going on here. Between 0, x equals 0, and actually x equals 5, which we certainly can't see the tops of the graph, the f function is growing, as is the g function, but that's growing faster, and the h function is growing the fastest. So that is why the green f function, x squared, isn't as steep as the blue x to the 4th and the red x to the 6th. Now what I'd like to do is I'd like to focus in on the flat part of the graph. And so now I'm going to go from 0 to 1 with a tenth as our increment. And check this out here. I'm zooming in. There we go. And look what's happening here. Again, we see some of the same numbers that we saw before. F is growing. It seems like maybe it's growing 1, 4, 1 100th, 4 100th, 9 100th, 16 100th. So it is growing. But what's happening is that F compared to G compared to H, you'll see that the G and the H function, the x to the 4th and x to the 6th, when you exponentiate small numbers, numbers smaller than 1, they're going to get smaller. So even though they grow, they are smaller versus the lower powers. And so that's why some students might describe this as the 4th and the 6th power are flatter in the middle. X to the 4th and x to the 6th get flatter. So going back to the worksheet, the lab sheet, is students are being asked to examine the different situations, use the slider to graph the different functions. What are the patterns you observe? What would the degree do to the polynomial? How does the sign of the leading coefficient affects the graph? And then can you come up with a reason why the graphs do what they do between x equals 0 and x equals 1? So those are some of the questions that I asked students. So there's 2 parts to this. There's the graphing using the graphing calculator, and then there's the pre-made GeoGebra file. And you'll notice that some of the questions are down at the bottom. Questions are really, really important. What you need to do as the educator is you need to ask targeted questions so students reflect on what they are observing. Let's, whoops, sorry, wrong thing. Let's go back to this. Here we go. Here are some of the good questions that I'm going to ask students to think about. I say to students, what will happen if? So what would happen if x was to the 12th power or to the 20th power? Or what must I change to make a certain thing happen? So what must I do to make the left side of the graph be up and the right side of the graph be down? How is one thing affected by another thing? What changes? What stays the same as we make changes in our environment? When will something be true? Why does this happen? Question shells are when you basically have fill in the blanks. It could be something like a polynomial graph with a blank degree has blank end behavior. And the last thing is to reverse the order of representations. So sometimes I want to begin with a graph. Sometimes I want to begin with an equation. Sometimes I want to begin with a table of values. If you don't always go into the situation, if you always go into the situation the same direction, if you always begin with an equation, then a graph, then a table of values, students don't get as adept at transferring between those representations. Okay, let's go on to our next activity. The next activity is a slope-intercept form. And this one is, pretty straightforward. If you want to make one of these by yourself in the Google Drive, where all of the materials are going to be, there's going to be instructions for how to set up checkboxes and how to set up sliders. By the way, in the Google Drive, I have PDFs of these activities, but also Word documents, because I want you to be able to edit them and change them to make them work for your students. Okay, so here, this is just a slope-intercept form. I've got my slope slider doing this. Here's my slope slider. I've got my y-intercept slider. I made a choice to make my y-intercept slider vertical. If you want to reset the construction, you click on these two arrows over here. And again, I want to ask targeted questions of students. They can play around with this, but let's look below at some of these questions. What does the value of M do to the graph? What does the value of B do to the graph? Make predictions of what will happen if certain conditions are met. So students are asked to engage in the activity. What happens with M if I make it more negative? What happens with M if I make it more positive? You can also, in this particular activity, enter values. So you can enter a slope of 1, and the graph and the slider will change to that value. You can enter a slope of 2, slope of 3, slope of 4, slope of 5. So I would ask students, what is happening as you're making this change? And students would say, perhaps it's becoming more steep, or it's, you can do it, that most students are going to say it's becoming more steep. I chose to show the grid lines here because let's say we have a slope of 3. Students can actually visualize, let me change my y-intercept to something nicer. Students can actually visualize going up 3 and 1 to the right. Students can show their equation, and so they can see where these values live in the equation. The last piece of this one was I wanted students to also have the opportunity to look at a perpendicular. And I like this one where I have it right now. I've got a slope of 2.5. I might consider updating this activity to have a fractional version of the slope so students can see the change in the y value over the change in the x value, the change in the vertical over the change in the horizontal. But what's really nice right here is if I ask students to count boxes to figure out the slope, let me make my B -1 so I have a little bit better view. Okay, if I want to look at the slope here, my slope is 2.5. That is 2 boxes to the right and 5 boxes up. So 5 over 2, because it's a vertical change over the horizontal change. And then ask students to examine the perpendicular. What is the slope there? How many boxes can we count? So it's going to be down 2 and to the right 5. Now, students who are just beginning, let's say in algebra, that's going to be hard for them to examine. So I might do something simpler. Let's look at a slope of 2 and a y-intercept of 1. What do the slope works out to be? The slope here is to the right 1 and up 2. And the slope of the perpendicular is down 1 and to the right 2. So students can begin to develop an idea, a conjecture of what's going on. Now, there are hundreds and hundreds and thousands of GeoGebra activities out there. When I've made these, I've been trying to target a particular learning. And like I said earlier, getting students to get all the way to the reflection part of the cycle is what's going to make their learning deeper and more durable. I've been victim of a really well-planned lesson that students worked with technology. And then, a week later, I say, well, what do you remember? They had a question for me. What do you remember? And they say, well, I know we did something on the computer, or I know we did something on GeoGebra, but they may not remember the actual math lesson that I wanted to teach. So the really important thing for me for getting students to get into that reflection cycle is to hold them accountable for making their thinking visible. And so there's a couple of parts to it. I require students to record their observations. I said earlier, it can be on a lab sheet or in a notebook or on a classroom chart paper or on the board or with a partner. There's lots of ways to do it, but it's really important for students to go through that cognitive, the cognitive demand of writing down what they see, put words to that. In order to do that, it's really important you give students some individual think time. And actually, this is lower down on the slide. So actually, I'll jump down to the bottom of the slide here. Use wait time. Don't steal another student's chance to reflect by talking too soon. It's really important to give students the moment to jot down their thoughts before they share with a partner, before you ask for input for the class. Another way you can hold students accountable for their thinking is ask them to restate and clarify a student's thinking. Perhaps the teacher does that restating, but it's even more powerful when we are in a group environment to ask somebody to restate what somebody else said. Or if you think a student isn't quite there, you can say, can anybody add on to what the other person had said? Another way you can do this is to compare and contrast one person's reasoning with another's. Do you agree? Can you convince me? And prompt students for further participation. Does anyone want to add to that? Okay, so I've got a couple more activities in the dynamic graphs. We've looked at power functions. We've looked at slope-intercept form. Now let's take a look at function transformations. This one is one that I created after somebody else had created it first. And one of the best ways to learn GeoGebra is to try to replicate an activity yourself. And what this function transformations activity does is it takes any parent function that you want to put in the input box, and it asks you, what do the parameters a, h, and k do to this function? So beginning with a parabola x squared, let's take a look at what happens when we change a. And there's a whole lot of stuff that is just going on with a. What happens as a gets bigger? What's happening to your parabola? What's happening as a gets smaller? And again, like I did before, I have an input box. So if you don't think that if the slider isn't going the way you want it, you can go from 0.9 to 0.7 to 0.5. To 0.3. Well, it's getting wider now. What happens when a is 0? Where's my graph? It's right here. It's down on the x-axis. What happens when a goes negative? The parent function has an a value of +1. What about the a value of -1? What does that look like? I'm just going to move H over a sec. Oh, let's just do it by the input box. Okay, so now you can take a look at +1 and -1. Here are the parent function and the transformed function. The lab sheet that goes with this, the questions that are at the bottom of the GeoGebra activity are just generic, what patterns do you see? But the lab sheet, hold on, here we go. The lab sheet asks students to now graph several functions. What I like to do is I like to have students begin by observing a mathematical consequence, reflect on it. Does A affect the shape, location, or orientation of the graph? And then apply their knowledge. So they're going to graph these functions with the GeoGebra activity as their tool. Some students might be ready to predict what they're going to look like. But here they are, they're examining it, they're interacting with it, and they're going to get a whole bunch of different graphs going on. This particular sheet has a graph grid on it, but you might want students to just do it freeform because it's not about having a precisely drawn graph as much as it's having students demonstrate the differences between the graphs. Okay, then the students are asked to adjust H and K, see what happens to H. Ooh, what's H doing? And what's happening to K. And then on the lab sheet, it's asking students to give a possible pair of equations for these functions. What's the relationship between them? What's an equation for this function? And this function transformations, like I said, is really powerful. I can put in a whole bunch of other parent functions. Other exponents, other bases, square roots, cube roots, absolute value. Let's try a few of those. Let me move my H and K back to something a little bit easier to deal with. Okay, so let's try absolute value of X. You can just type abs X, whoops. Okay, and you can do the same thing with absolute value. Square root X. And you can take a look at what this is doing here. And let's also do, what fun one should we do? How about X cubed? Okay, because again, A is going to change that end behavior when it shifts from positive to negative. So there's a lot of fun, deep math you can do here, and you can have students working with whichever parent function you'd like them to work with. We're getting close to the half-hour point here. I want to finish up with our last of our dynamic graphs. Let me just quick see if there's any questions in the chat. So if there's anything that you want to ask before I move on to the next one, please jump right in. Okay, here is rational functions. And again, I was basing this on A, H, and K, but I was really interested in what students can take from this. So students who've had experience with A, H, and K will notice that A, H, and K are going to do similar things than they did before. If we show the asymptotes, they can see that H is going to continue to be a horizontal translation. And K is going to be a vertical translation. And by the way, I have this checkbox showing a specific function, which means that they don't just get the structure, the parent function, they actually get the values, and they can see where these values go. H is 2, let's make K -1. A is a little bit different. They learned in the other function transformation that it has to do with vertical stretching. Here, it doesn't feel like it's a vertical stretch to students because it feels like it's moving away from that origin. But indeed, it is a vertical stretch. If you focus here right on a point, actually, let's move A downward to here. If we focus on a point right here in the curve between 2 and 3, let's call an x value of 2.5. Watch that x value of 2.5 as A increases. Now it's all the way up here. It's about 1.5. X value of 2.5. Where is it now? Oh, it's up to about 4. X value of 2.5 is now off my screen. Okay, I don't think I can, I don't think I set it up so students can grab this screen. But that A is still stretching it. It just looks different with a rational function. As A gets really small, it approaches the asymptotes. And then when it goes negative, it switches to the other quadrants. Okay, and let's check out the lab sheet for rational functions. Like I did with you, the lab sheet asks students to change the values of H and K first. I don't think that's big enough for you to see. We're going to change the values of H and K first. And the reason why we're going to do that is because my students were already experienced with H and K. Sorry, trying to get this bigger. There we go. Use the sliders to change the values of H and K, observe the changes on the graph, make a sketch. Where is the point HK, actually? So the point HK, you might notice here, is the intersection of the asymptotes. Now adjust parameter A. What happens to the graph? How does the graph change? So your students might not approach it the same way. You may get into rational functions a different direction, which is why the activities that I'm sharing with you, I'm giving it to you as a PDF as well as a Word document. Now let's change the exponent in that denominator. Instead of it being a denominator of x to the first power, or the factor, the linear factor to the first power, let's make it the second power. Let's rearrange some stuff here. And by the way, if h is 0, we're going to end up with just an x in the denominator. Okay, but this whole graph has a totally different shape. It looks more like a funnel going up, or two sides of a very, very steep mountain, if you will. And A still turns it upside down. But like we did before with the graph and the table, my question is, why are we getting this difference? Why are we getting both parts of the graph heading up, whereas with n equals 1, one part of the graph is heading down? Let's head back to our graphing calculator. This is the one we did before. Okay, and let's take a look at, what do we have here? 1.3 over x minus 2 squared. I'm going to make it pretty simple. Okay. Let's zoom out. Here we go. So here is 1 over x minus 2. I don't have a vertical translation. I do have a horizontal translation. And now let me get the same thing but I want it to be x minus 2 squared. Okay, so the first thing that's really interesting when you look at it with the graphing calculator is that students might think that the two first quadrant sections are going to be the same, and you can see that they're not the same. And that's because when you take the denominator to the first power versus the denominator to the second power, you're not going to get the same values. And like I said, my question for students would be why? What can you do to explain to me why this left side of the graph is above the x-axis, if you will, and the right side, but with the non-squared denominator, it's below the axis. So let's take a look at the table. Let's do from -3 to +5, let's say, or -5, let's step 1. Okay, and going back to the calculator part, I'm going to add Q to my table of values. And the P function has the denominator to the first power. And when you have a denominator to the first power, the negative values are negative. The negative x values, excuse me, it's a little hard to see this. Let me pull this over here. The negative x values give negative y values. The positive x values give positive y values beyond the asymptote. And whereas the squared denominator, all of those values are positive. And students might have to look at the table of values to think this through. Okay, this denominator here, when it's squared, it's always going to be positive. The P denominator will be negative if x is smaller than 2. So this table of values idea really gets students to dig deep into why the graph looks the way it does. So I'm looking at the chat, and Andrew is saying that students think that H means horizontal, and that might be a hesitation. So I've thought a lot about what to do to get students to think graphically. So for example, I talk about graphs that have, I talk about things that you move in the x direction, let's say. If you're going to do a reflection, let me clear some of this out or get another one. So if I'm going to take x squared, and then I'm going to do x minus h squared. Okay, so this 1 is my h value. And students have difficulty sometimes because there's the negative there, so you're subtracting the h value. But what I say to students is that the h value, they identify it as a +1. That means I'm going to move 1 in the x direction. I'm going to move 3 in the y direction. Okay, so I use the words move in the x direction, move in the y direction. I don't talk much about, will you take the opposite of this number? I talk about how h is 1 and you move 1 in the x direction. If this turns into x plus 1, well, what's my h value? My h value is -1. It's x minus -1, and I'm still now moving -1 in the x direction. So the words you use in your class are going to be merely meaningful to students, and I try to use words that have to do with the direction that they're moving. We stretch in the vertical direction. We translate in the horizontal direction. Okay, so that's what I've got here to share with you tonight with the dynamic graphs. There are many more that you can do, but what I want to do now is I want to move along into invariance. And so what do I mean by invariance? I don't even think I have this in a slide. Okay, what I mean by invariance are something about a mathematical situation that stays the same while other parts of the situation change. So that could be a measurement, a calculation, a shape, or a location. And these are really, really powerful ideas for students. And we see them often in geometry, but that's not the only place that they show up. And let's take a look at the first one of these that I have. It's angles in circles. So this is something here where we teach students about central angles, we teach students about inscribed angles, and we don't always talk about it in a dynamic way where students can, like I said before, act on the mathematical situation, observe a mathematical consequence, and reflect on the mathematical meaning. So first of all, I began here with, what do you notice about this diagram? And can you complete these statements about the angles? These are what I call these sentence frames. This is where students are basically filling in what they know about the vocabulary, and it gives you as a teacher an opportunity to remediate or just make sure you're all on the same page about what the vocabulary and the definitions are. Okay, so we're going to ask students first to grab and move point C to several locations. So what's happening when you grab and move point C? Let me get to a good place. There we go. It's not going to be exactly perfect because of pixels. Let me see if I can get to a really good one. There we go. Okay. Angle B is 55.32. Angle AOC is 110.64. What do you notice? And students are being asked to make a conjecture. Jot it down on your lab sheet or talk about it with your partner. Next, I want students to grab and move point B, and notice what happens. And this is actually kind of surprising to some students. Nothing's changing. Now, it may not be surprising to them that the central angle doesn't change because that's not moving, but why doesn't angle B change? And I deliberately ask students to move point C first. Andrew's commenting that what my comment about it won't be exactly right with the pixels. There are rounding errors in everything we do, and there are some times where we can avoid seeing them, but you know, let's see if I can get to a place where I had a rounding error. There we go, 54.32 and 108.63. These measurements are being calculated to more decimal digits, but somewhere when I rounded it off, it's not going to be exact. And by the way, you can copy these activities. They're public on my GeoGebra page, and you can adapt them. You can change the level of precision. So if you don't want your students to have two decimal digits, you can make it 1 decimal digit. So you can do what works for you and your students. In any case, it was a deliberate choice to have students work with the movable one first, rather than the one where nothing changes, because I want students to realize that this is dynamic. These numbers aren't just a single measurement that we might do with a protractor. These are things that are changing. And that's actually the power of all dynamic technology and geometry technology, is we are getting infinitely many instances of a scenario every time we drag and move. And so what you want students to do when they're engaging with dynamic technology is you want them to drag and move. And then what changed, what stayed the same, what did you observe? Okay, so what we've got here is we've got students hopefully are conjecturing that the central angle is going to be twice as big as the inscribed angle. And so now we will let them show that ratio. And this ratio shows up as 2. But what is nice about this, students may not realize that 2 is being dynamically changing. It doesn't change. This is the invariant that we were looking for. Okay, so what is the relationship between the types of angles shown in this diagram? Does it hold true for all locations of A, B, and C on the circle? Well, maybe it does. Students can investigate what happens when we get bigger than 180 in the central angle. GeoGebra is going to let us measure that reflex angle, that angle bigger than 180, although many of our curricula may not deal with it that way. And certainly the central angle on this side is the central angle that we know and define it. So the activity doesn't restrict students from doing that. Some other geometry programs will automatically measure that angle on the other side. It will only measure a 180 or less. The last thing that I ask here is to ask students to move point B so center O lies on segment AB. So move point B here so that A lies on this segment. Here we go. There we go. And this setup is a setup that could allow students to prove their conjecture. Now, your curriculum may or may not be focused on proof, but if it is, it invites students to go ahead and prove it. Showing it using dynamic software is not in itself a proof. It's a confirmation that something works, but if you want to teach deductive proof, then go ahead. Okay, next, my all-time favorite, interior and exterior angles of a triangle. I've done this activity in every kind of software that I've been lucky enough to do. And what this activity shows is it's going to have students collect some data. So I want them to record several sets of measurements in a chart. And I'm going to show you the lab sheet. That chart is in the lab sheet. Okay, let's make this bigger. Okay, here's the same thing in the lab sheet. Here's the recording chart. If you are working with students in a remote environment now, what's lovely about GeoGebra is you can send out the link to an activity and have students submit their work to you, but the activity was remote and available freely on the internet. Okay, so record several sets of measurements in the chart like this, and we're moving point B. And in the classroom, I would ask students try to make a right triangle, try to make an obtuse triangle, try to go the other way. And you want students to make some recordings, record some of this data. And I actually struggled with this a little bit about putting it up here. When I did this in the classroom, my next question was, what do you notice about the angle measures as the shape of the triangle changes? And I didn't give them any hints. I just wanted them to look at their chart and what do you notice? It's not obvious to students everything I want them to notice. You know, we're the teachers, we know what we're looking for. So we know that the three angles of the triangle add up to 180. We know that that's the answer we're looking for. How do we get students to get there? Sometimes we give them hints, but I liked to ask students to play with it and see if they noticed it. This lesson always came after they had already learned the three angles of the triangle added up to 180. So that part they had in the bag, but then I wanted them to figure out some other things. I wanted them to notice some other things. And here we go. I tried really hard not to give them hints. I would say, what other angle pairs would you like to add together? And I made that deliberately vague because I wanted students not necessarily to be told which ones to add up. So some students might want to add these two angles up, the interior angle and the exterior angle. They should be a supplementary pair. Some students realized that the two remote interior angles do add up to the exterior angle. Other students might have gotten off track and not really known where to go, but if you give students hints without giving it away, they can own that learning. So I would say to them, pick two columns to add up and see what happens. So you and I, as the teachers, know that if you added up angle CAB, angle A, and you add up to angle B, so if you add this first column and the third column, it's going to add up to the fourth column. But if you just give students the direction, add up individual columns, try picking them, see what happens, they might be able to discover it themselves. What's nice about this is I was able to put a checkbox, show the sets of angles to add together. So here, color coded, and a shout out to my good friend Steve Phelps for helping me figure out how to color code this. Show the sets of angles to add together. To add the green, the purple, and the yellow angle together, that is the 3 interior angles of a triangle, and that's going to be an invariant. It's not going to change despite the fact that I am changing my triangle. The green and the purple is the 2 remote interior angles. That's going to change, but it's going to match that exterior angle. And then the BCA and BCD is another invariant, 180, that doesn't change. Now, when I was working in the classroom with students, there was always a student who was finishing fast. And I've been doing this on calculator technology, on laptops with students in one-to-one devices, or in a computer lab back when students didn't have one-to-one devices. And you know those kids that are finishing fast, they're off to YouTube and they're doing other things that they aren't necessarily supposed to be doing. So every lab sheet, I tried to add an extension activity for fast finishers and students who needed to stretch. And so the the question here is, what would happen if you put an exterior angle at every vertex? And so this checkbox allows us to add exterior angles and ask students, what's going to happen now? Okay, so again, we can still move point B. Let's see if we can get to pretty numbers. Oh, those are pretty numbers. And showing the sum of those, that's going to be 360. And the question is in the lab activity as well. List the measures of the exterior angles of your triangle, 1 at each vertex. What is their sum? Why do you think it's important to use 1 exterior angle at each vertex? And you can decide, is this something you want all your students to do, or is this number 6 an extension for kids who need that extension? Number 7, asking students to apply what they've learned helps them to solidify their knowledge. I also would have students make one up. So here you see, find the missing angles in each diagram, then create and solve your own. Okay, last one for the night, right triangle ratios. Those of you who might be in Algebra 2 or Trig, here what we're doing is we are dipping students' toes into what's going to happen when we take ratios of sides of a right triangle. And we're going to begin here by grabbing and moving point F. Now, why am I choosing to move point F? When I move point F, everything changes. And I really want students to recognize that they're in a dynamic environment. Everything's changing. This makes it much more powerful when we get to an invariant. By the way, you can go to special places with F. Let's see if we can get F to be at 45 degrees. Well, pretty close, almost 45 degrees. And notice what we've got in the boxes above. Let's try 30 degrees. Can I get there? Oh, pretty close. Okay, so at 30 degrees, I've got one set of answers, 0.5, 0.87. What about 60 degrees? Again, 0.5 and 0.87, but they switch places. Interesting. I actually have another activity that shows that better. Okay, at any rate, move point F. What measures stay the same? What measures are changing? What ratios change? And look at the triangles. What happens to the triangles that are created as F moves? Are they similar or not? So this is asking students to think about these triangles. Are these triangles similar? No, they are certainly not. Then the activity moves on and asks students to now move point C. And we're going to get a very different situation. As we move point C, some side lengths are changing, but the ratios are not changing. Okay, what is the measure of angle B? And explain how you found this. So students can subtract from 90. Angle B is the complement of angle A. What ratios change? None of the ratios change. Let's go back to a 45-degree angle. Okay, so even though my triangle is changing, none of my ratios are changing. These are similar figures. Students are asked to explain their thinking, think about why this is happening, and there is so much more you can do with this. If you are really interested in the idea of the complements, those of you who are doing trig and pre-calculus, I'm going to jump out of here. And if you see my full GeoGebra page, I've got another book of Action Consequence that has more activities than the ones we did tonight, but I just want to grab one of them. I'll stick it in our box as well. Right triangle invariance. This one here is really focused on the idea that the two complementary angles, excuse me, the two acute angles of a right triangle are complementary, and that those add up to 90. And this one I set up with a spreadsheet. So I can change my data here, and I can make angle A 46 point, whoops, I lost where it was. I don't remember what it was now. There we go. 46.16, and angle B is 43 point, actually, I guess it's 46.17. You'll indulge me here, 43.84. And in this spreadsheet side, I can fill down and find the sum, and the sum is an invariant as well. So I chose to do the invariance in a spreadsheet. And then what happens is if we take the sine of one of the angles and cosine of the other, we'll notice that the sine of one angle, one acute angle, is the cosine of its complement. Very interesting idea. This gets sort of glossed over in pre-calculus if you're still doing trig identities, but it's a really interesting invariant, and it's another fun one that I will put in. Okay, we've covered an awful lot of ground tonight. Let me just give you a couple of things that you will need if you want to reach me. Here we go. Okay, actually, that's not where I want to go. Look, I've got it right here. Here's how you can contact me. It's Karen Camp, karen.camp@gmail.com. My Twitter is @KarenCamp. And I blog intermittently at karendcamp.wordpress.com. The Google Drive folder with all of the Word documents and PDFs of the activities, along with a couple of tutorial items, how to build a slider, how to build a checkbox, and a brief tutorial on the GeoGebra Classic is also going to be in that Google Drive. If you are new at this, I created these in GeoGebra Classic, and would love to hear from you. If there's anything that I've left out or forgot to put in the Google Drive, please send me an email. And Tim, I'm not sure, I haven't really been able to look at the chat because I was doing too much else, but are there any questions that have gone by that I haven't been able to answer?
Not that I saw. So, I mean, there's a couple there. You could check out the end. Andrew made some pretty interesting comments, but other than that, no, it's pretty cool. Thank you.
Thank you, Andrew, for paying close attention. And one of the best things about interacting with other teachers, if you have a colleague that is willing to do this with you, have them try your activities, have them give their input, because that's one of the best ways to know if it's going to work well with students. And you can't predict everything a student's going to say, but together with a colleague, you can do a really good job.